Hey everybody, this is your first lecture that has been pre-recorded for you guys to come back and enjoy as you further go. This lecture is on homeostasis and on regulation of feedback loops. Enjoy. Welcome to your lecture, and today we're going to be talking about tissues, fluid compartments, and self-regulation. So essentially what we're going to cover is we're going to talk about some of the tissues, the organs, organ systems, their names and functions. And this is going to take place throughout not just this lecture, but several lectures as we go along. We're going to talk about the fluid compartments and their sizes today. We're going to explain homeostasis, steady state, and equilibrium. And we're going to talk about the components of the reflex loop, as well as we're going to contrast both the local and distal reflex loops. We're going to explain the positive and the feedback loops, and eventually we're going to talk about tonic and antagonistic control, and we might tie in some circadian rhythm. So in the beginning, our body begins with this single fertilized egg, and that undergoes cell division and essentially eventual differentiation. So the differentiation. This essentially is a process that allows our cells to develop and become specialized. And the specialization will begin to perform a function. And cells that really work together to perform a specialized function develop into something that we call tissues. And we have 4 types of tissues in our body. And these tissue types will form organs that perform even more of a specific function. So we have our muscular tissue here. We have our nervous tissue. We have our connective. And then we have our epithelial tissues. Now, if we have several organs functioning to perform a kind of this specific task all together, they're really called an organ system. So, for example, we would have the kidney as the organ. But if we add in a few more, like the kidney, we have the ureters, bladder, and even the urethra, we get what's called an organ system. Now, there's 10 organ systems in the body, and really overall, for the next several weeks, we're only going to cover about 9 of them. Okay, and these systems perform very, very specific functions. And there's kind of 4 main functions that all of our organ systems are divided up into. And the first of those is a barrier. So what can we think of in our body that would perform a barrier? Obviously, that would be the skin, right? That's the first thing that typically comes to mind. And this is protective. And it's hydrophobic, hence the protection. And what this means basically is it keeps the bad out. And then it has the entry. We have an entry component. And this would be our respiratory and our GI tract. And this is for the exchange of oxygen, carbon dioxide, and nutrition, respectively. Thirdly, we have transport. And transport, the most obvious one that we know of is cardiovascular. And really, this is to move nutrients and or oxygen around into the body and remove and coordinate some of that removal of all of the bad stuff out. And we're going to talk about this in a little bit more depth at a later on. But another action or part of transport is diffusion. You might not think that this is actually part of an organ system. However, it's law of diffusion that plays as a portion of transport in our body. So, well, once the nutrients kind of get to where they need to be because of our cardiovascular system, they need to be able to move out of that cardiovascular system and get to the cells that are kind of on the outside. For instance, our skin. So if you can see here, we have the vessels that kind of end almost here. And so all of these cells here are still live tissue. They need to get oxygen and nutrients. So those are going to diffuse across these membranes. So diffusion, in essence, is a transport system in of itself. And finally, we have a way of getting things out of our body. And we know this in the renal, the GI, and yes, also the respiratory tract, right? We must be able to remove the wastes and that we accumulate and byproducts of our body metabolism, such as excess ions, water, waste, etc. So cells are like mini me's just inside of our body. And just like the skin, or just like the skin, cells have this hydrophobic bilayer. And we were kind of talking about this a little bit yesterday in our discussion. So we're going to get a little bit more in depth into it now. And really, what this lipid bilayer we have these phosphate tails. Sorry, not tails, heads. And these phosphate heads are also attached to a glycerol chain. And what the glycerol chain is basically a backbone, and it sits kind of right at the bottom of each one of these phosphate heads. Okay. And what these do, this basically acts like glue. And what it does is it holds these fatty acid chains, and two of them on each one of the phosphate heads, in place. So that's exactly what we're kind of looking at here. So if we can actually blow this image up, this is essentially what we're looking at. And then of course we have our rather large protein channel. And so this is our water loving area. These guys love water. Okay. The difference is these guys underneath don't like water. Okay. So no H2O. So we call this hydrophobic. So the reason why the top is more hydrophilic and loving the water is because the water in our body, in the version of plasma, carries a lot of our nutrients. And we want those nutrients as close into our cells as we can get them so they can diffuse across. So these phosphate heads obviously want to love the water and draw that water in. The problem is we don't want everything just going inside the cell. So we need to modulate it somehow. And so we have this lipid bilayer, and that basically sits as a reverse on either side. And these hydrophobic areas in the middle basically keep out all of the bads. Okay, they also don't allow ions through. They don't allow a whole lot of different things through. And we're going to actually talk about that a lot more in depth in your next lectures. Okay, so as we said, cells are like mini me's inside our body, and they have multiple different compartments, and they have different components within those compartments. But in essence, when we're talking about fluid in our body, what we mean is we're talking about the fluid compartments. And we're really broken down into two compartments in the body. And we call that our extracellular fluid space, ECF. We call that our intracellular fluid space, the ICF. So a couple of things to note about these is the ICF is 2/3, that was not what I wanted to do, 2/3 of our total body water. Whereas the opposite of that, the extracellular fluid, is 1/3 of our total body water. And these two components, they're not really equal in what they have in components within inside them. And when we're talking about the total body water of the intracellular fluid, what we're really talking about is all of the cells put together. We're not talking about just one or two cells, obviously. So for the sake of generalization, what we're really referring to is we're talking about one cell in specific, but we are referring to all of the cells in the body. Inside our cells, it is primarily potassium dominated, and it has actually very little sodium. In the opposite of that, we actually have a lot of sodium on the outside of the cell, and we have very little potassium on the on the outside. So they're almost a mirror of each other. The one main difference is that on the inside of the cells, we have a negatively charged ion in proteins. So these guys are actually quite important when we talk about propagation of action potentials. These are super important to understand. That is primarily negatively charged because of these protein ions that sit within the cell. And the cell itself is, as we know, is separated by this plasma membrane, okay, as we can kind of see here. All right, now if we take all of the components that make up each of the cells and all the components within those cells and the fluid component of that, the fluid component we call cytoplasm. And we put this into one compartment itself, and that we call the intracellular fluid. Now, the space immediately outside of the cells we call the extracellular space, and this incorporates the rest of the fluid makeup of the body. Okay, now these two compartments, as I said, have a very dissimilar components to them. Now, we can further divide our, uh, our extracellular space into two components. We have the intravascular space, so within our blood vessels themselves, and we have our, we even call it the extravascular space or the interstitial space. Okay, and a lot of times, actually, what we call this is the extracellular matrix. Is kind of this component here, and the interstitial space is not necessarily filled with fluid, but there is a water component to it. Now, the intravascular space and the interstitial space have the same components. Okay, so there's an equilibrium between the two. We have a fair amount of sodium on either side, but we also have the same amount of potassium on either side, as well as, chloride ions. We also have calcium on either side, right? So basically all the components are the same on either side that you work on. Now, the intravascular fluid does contain protein. Now, that protein itself isn't free floating like it is inside this cell itself. It's actually in the form of albumin. And albumin is the primary protein, but usually albumin is attached to another component, and this actually acts as a buffer system for hydrogen ions. So a lot of times albumin itself is plasma bound. It's bound into another ion in some way, shape, or form in order to buffer out our systems. So albumin we don't count as a charged ion within this space. We'll talk about albumin a little bit more in depth and a little bit further down the road. All right, now lastly, there's this disequilibrium between the intravascular and the interstitial space. Or sorry, there's this equilibrium, but there's this disequilibrium between the extracellular and the intracellular space. Now, this is maintained by something that we call steady state. So what a steady state is this is referring to how your body's cells are able to maintain this disequilibrium between them. And so this is done by an enzyme called ATPase. So we can see in the video here that this is the ATPase right here. Now let's use a different color. I think yellow might show up better. Nope, not really. Right then. So this is the ATPase. What's going to happen is it's going to utilize ATP in order to move the potassium back into the cell and the sodium back out of the cell. We're going to talk about this a little bit more in just a minute. That's essentially what this is referring to. Okay, so this is an enzyme itself that utilizes energy in order to move those around. Now, ATPase cleaves the ATP. So if we want to think about it, what it does is basically kind of like a big kitchen cleaver and chops it in half, and that produces two ADPs. These are the energy sources for the ATPase. Okay, now this enzyme is activated primarily by ions, and it's moving against the gradient. And because it's moving against that gradient, that's why it requires energy. Okay, so why is this necessary? Well, picture this. You're sneaking out of your house, right? Now, you're not supposed to, but there's walls, there's doors, and they all keep you inside the home. But as we all know, there's also windows, and windows you can get in and out of. So kind of like our cells, they're just a little bit leaky. And so every once in a while, we get a few of the sodiums somehow manage to get themselves inside the cell here. And just like the potassium as well, potassium wants to do the same and sneak out of its house, and it's going to outside of the cell. But typically, the ratio is for every two potassium, or sorry, for every two sodium, for every two potassium, 3 sodium go in. Okay, so the exchange typically is 2 to 3. And this is going to become very important when we talk about propagation. Okay, it's going to become super important when we talk about that. All right, so let's say we have let's put this into an example. So let's say we have a 70 kilogram male. And we know that approximately 60% of our body weight is water. All right, so therefore, a 70 kilogram male is going to have a whopping 42 liters of water. Now, let's consider this for an example. We know that the intracellular fluid compartment, so all of the cells, is 2/3 of our total body water. So that's going to equal 28 liters. Yeah, that's right. Our cells have 28 liters of water inside their components. The extracellular space we know is 1/3, and that is still a large 14 liters. Now, remember how we were able to divide the intravascular and the interstitial space. So this can be further divided into 1/12. And really, 1/12 of this is your plasma. So in essence, our extracellular fluid volume is 1/12 of 14 liters, which really isn't a whole lot. So we know that's around 6 liters. So we really truly only have 1/12 of the actual amount of water that you normally think of as fluid in our body. Kind of weird to think about, isn't it? All right. So now we're going to talk about self-regulating mechanisms. So what are self-regulating mechanisms? Well, self-regulating mechanisms. What's happening here? That's not what I wanted. There we go. Okay. So self-regulating mechanisms are mechanisms that exist between two compartments. Okay. And they're active mechanisms. Okay. And what they are is there's an equilibrium, and their goal is to try and maintain a balance. And active mechanisms that we know of that maintain an equilibrium, and this is the symbol for equilibrium, there's an amount of substance and there's a specific amount of substance between the intravascular and interstitial spaces. Okay, so there's a specific amount of that substance. And what we're talking about is sodium, maybe some potassium. We're talking about chloride ions, glucose, and so on and so forth. And this is distributed between the two compartments. So it's equally distributed between the two compartments, the interstitial and intravascular. There's no net transfer between the two compartments, and there's no barrier between them, no barrier between the movement or to the movement. And finally, there's no energy expenditure. This is just my shorthand for energy. And there's no energy expenditure for it to maintain the equilibrium. That should be a little bit more clear. Now, in contrast, and what I should be more clear of this is what we call equilibrium. Okay, so even though we're talking about several times, this is the equilibrium component. However, in contrast, in steady state itself is present between the extracellular fluid and the intracellular fluid. So it's comparison between the two. And there's a consistent amount of substance on either side. So it's consistent, not the same. Okay, so that's very important to understand. So it's consistent amount, not necessarily the same. Okay, the input must equal the output. The concentration between the two compartments is not equal, and it requires energy. So this is the use of ATP. And that's how you can differentiate between the two. So really, what is homeostasis? why do we care about compartments? And I know that this is kind of a common theme in physiology. And really, it's homeostasis is the even balance or the equal, it's equality on either side. Okay, it balances the in with the out. Okay, and the reason is cells require a very specific set of factors in a very narrow range, in a super narrow range. And these are substances such as oxygen, carbon dioxide, hydrogen ions, temperature, glucose, etc. And all of these substances need to be maintained in this kind of set point. So this range, and we'll even call it a set point. And we take in a very, very diverse amount of substances on a daily basis. For example, let's say you eat a lovely little hamburger. Well, this hamburger has fats, it has protein, has carbs, oh, the evil carbs, and has nutrients in the form of minerals and vitamins. Now, it gets digested and goes into the bloodstream from the GI tract to all the cells. Now, our body, organs and organ systems, they're trying to maintain this buffer system at all times between the ECF and ICF, and that very narrow range. And we call that in the range compatible with life of the cell. So the maintenance of this steady state is the overarching theme in physiology. This is what homeostasis is all about. It's maintaining this balance. So what happens if we can't maintain a steady state? Well, let's look at the normal. If our input matches our output, essentially we're in a state of wellness. Okay, so this is everything within the cells, within that narrow range. Life is grand. We are happy. However, if our input supersedes our output, or even the reverse of this, and when our output supersedes our input, we get illness or pathology. Okay. Now, if the organ system is not maintaining the steady state, we get that mismatch. We have a mismatched steady state. Okay. So it's important to understand this. So how do we control this steady state? In order to maintain this steady state and have cells communicate that there's a change in input or output, to get itself to speak or back to its normal, we need what we call homeostatic control, informally known as a reflex loop or a feedback loop. Okay. Now, reflex loops have three main components. So, its first main component, we have a sensor. Now, this guy senses anything that is a stimulus, and it could be a change in temperature, pain, change in internal, external environment, what have you. But there's a sensor of some sort that detects this change. And it's going to send information to a specific center called an integration center. All right, so this integration center, and usually this is the brain. More specifically, it's actually the hypothalamus. This is where all of our set points are stored. All of our set points for organ systems, our cells, our internal environment, and our external environment that we can control. Okay, and these cells have the capability of determining within the brain, determining whether or not the incoming signal is above or below the set point, and then it's going to decide whether or not it needs to send a response. And so it's going to send its response. It's going to send its response to something we call the effector. So if we want to say it like this, the sensor has been affected, and the effector is the response. Okay, this is going to make sense in a second. Now, the effector itself is going to carry out an effect. It's going to do something to bring about a change. So it's going to elicit change to get everything back to its normal. In order for this to stop happening. So once we're back to our normal, these cells stop sending their signal up to the hypothalamus, and life is grand. Now, there's a couple of terms that we should understand here. The first term is the afferent pathway. Now, this is the nerves that travel from our sensors or our affected area to the brain. Our response going to the effector is our efferent nerve pathway. Okay, so these are really important to understand. And when we get into our nervous system components, these will be utilized a lot in our conversations. Okay. All right, so let's provide this in an example component. Think of the temperature in your home. You have your thermostat. Okay, and it is going, let's say it's going down. Your temperature has dropped. And your thermostat has sensed this temperature drop, and it's going to send a signal to your control center of the house, and that's going to send a signal to your heater. And that is going to turn on, and it's going to create heat. In the form of fire. Okay, so we got heat rising up, and it's now heating the home. Eventually, this stimulus is going to stop because our temperature goes back to normal. Therefore, this signal will stop, and our heater will turn off. Okay, very similar. We have a similar control system in our body of thermoregulation. Talk about that a little bit later. Let's consider another example here. Now, 1 week you're hunting for money, or you're hurting for money. We're all students. We've all been there. Heck, it's a pandemic. I'm sure some of us are out of a job. So we're really hurting for money. But you notice that Ichiban noodles are on sale for 10 cents a pack. So you buy about 100 of them. So given that, these are uber salty. So all your entire diet for 1 week is going to consist of this salty diet. Okay. So on Monday, our input is our diet. And our output is judged by our urine. So on Monday, our diet is equal to our urine, but we're just starting this Ichiban diet. So right now we are in a neutral balance, aka wellness. We are happy. All right, by Wednesday, we've been eating a lot of salt because of the Ichiban, but our urine, our output, is still the same because we haven't had a chance for those reflex loops to start kind of kick in and do that stimulus. So this we would call a positive salt balance. Okay? Or a negative urine balance, or basically a negative correlation between urinary output and diet. Okay? So it's not equal. Now, on Friday, everything, because of the feedback mechanisms, is back to normal. Our diet is equal to our urinary output. So our salt is now equated by fluid volume. So we're back to this steady state. Notice how I didn't say wellness. Okay, why is that? Why do we think that is? Well, let's think about it for a moment. Inside the body, we have an increase in sodium content. Okay, therefore, the body wants to maintain neutral. So what happens is, because of the law of diffusion, in fact, actually in this case, it's osmosis, because it's the movement of water to dilute a concentration. Okay, so what's going to happen is fluid is going to go from one cell into the interstitial or intravascular space. And the reason for that is, again, to dilute it, to maintain that concentration of balance on either side. Okay, remember that. The second part of this is it's going to trigger a mechanism to drink. We call this the thirst mechanism, the thirst reflex. Okay, so now our water input is equaling our salt input, and our body functions are going to maintain a normal input output. So it's going to force us to pee. Okay, it's also going to replace the fluid loss from the cells and the fluid shift. And again, that goal is to maintain that balance and dilution of salt to maintain that concentration on either side. So the content is changed, but the concentration has not. Okay, so the content has changed. However, the concentration has not. So, what does this mean in terms of our world? Well, if we have an increase in salt, we have an increase in water consumption, we have an increase in intravascular volume, and all of this is going to lead to an increase in our blood pressure. Hopefully, that's kind of making sense. So this component, we are going to talk about the regulation of homeostasis in fluid compartments. Now we're going to get a little bit more in depth into the reflex in both local and systemic control. We're going to define components of the reflex loop. We're going to explain both positive and negative, and then we're going to talk about tonic and antagonistic control. All right, so local homeostasis occurs within neighboring cells. So we always have two cells. I mean, all of our cells are kind of neighboring with one or the other at some point. So we have cell one. Actually, I'm going to erase this. So we have cell one, nice little nucleus. We have cell two. So it's relatively close to this guy. Okay. So cell one will secrete a chemical. So here's a chemical that he secretes. Okay. And this is just kind of what it would look like. And it recognizes the chemical within the cell. And the opposite cell, or the cell that's neighboring it, is going to have specific protein markers on it that are going to actually be able to accept those enzymes that it's producing. Okay. So, and this will cause a stimulation, or it will cause an action within the cell. Okay, whether it's an informative action, whether it wants the cell to produce insulin, or it wants its cell to, kill itself, which we'll talk about soon. But in any case, when one cell influences another cell, and I should say another cell's, activities, We call this paracrine. Okay? And it's actually called paracrine control. And when a cell secretes a chemical, so let's say this cell also has the same markers on it, and it secretes a chemical, and this chemical is going to come back around and it's going to act on itself. Okay? We call this component autocrine. The cell's influencing itself. So autocrine and paracrine controls are primarily in the GI tract. Also, another component of control, or sorry, local control, is the presence of what we call gap junctions. Oops. Gap junctions. And they're present to allow communications between cells. And what this is this is a free flow of ions between these two cells. Okay? And it's important, more particularly in the cardiovascular system, moreover, the heart itself. And this allows the cardiac myocytes to contract in unison. So this is how our heart is able to have that lub dub. They're able to contract in unison. So the top and then the bottom, and all of those cells are contracting at the same time. It's because of these gap junctions. And within the heart itself, we actually call them intercalated discs. Okay. And really, the most important component that is flowing through these is specifically in cardiac myocytes, and the muscle tissue itself is calcium. Because calcium itself is required for muscular contraction. So it's actually the flow of calcium itself that allows the unison contraction. So let's talk about reflex loops. And reflex loops are where the response is different. So where the response is distant from the target cell and the stimulus cell. Okay, so the target cell that can respond to a signal from the brain, and really, we're not talking about just one cell. Okay, so it's not just one little guy that we're talking about. We're talking about millions. So millions of local cells that are sending the signals themselves to the brain to say, "Hey, something's going on. We need action." Okay, so when we talk about one cell, what we're doing is we're actually just generalizing, but it's for the purposes of illustration. So I just want you guys to be aware of that. Now, there's two major communication systems within the body. There's endocrine or endocrine, and there is nervous. Now, the endocrine cell secretes a chemical and ends up in the bloodstream. Okay? So this little guy secretes a chemical, and we see these chemicals basically getting secreted. That's going to end up in the bloodstream and out to the body. Okay, and when it gets delivered, it's delivered or taken up by that cell by a specific protein. Okay, so it gets delivered, and let's draw another cell, and he's a little bit different, and he's got a specific protein marker for those cells that are very highly specific for it, and it's going to bring about that action. Okay, and they're basically receptors that are designed to recognize this. So an endocrine gland cell is regulating target cells by way of chemicals. By way of chemicals. Okay. Now, in contrast to that, and it's actually really not even contrast, kind of in consideration with that, we have our nervous tissue. And our nervous tissue has something similar to endocrine, but it's also similar to what we call gap junctions. So if we picture here, we have our neurons. And neurons will typically butt right up against each other in a super small space. And this gap junction space itself is actually called a synapse. A synapse. Now, just like the endocrine glands, these guys are going to produce loads of different neurotransmitters and chemicals. These chemicals are going to diffuse across the synapse. And on the other side of the synapse, you have your neuron that's going to accept it. Okay? And it has specific markers for different neurotransmitters. And each one of those is going to create a different stimulus. Okay? So we have our neurotransmitters that are going across. And neurotransmitters are things like acetylcholine, norepinephrine, serotonin, dopamine. Okay? And there's just a plethora more, but these are the kind of the main component ones that we're going to talk about in the future. So the neuron butts up against that other neuron or cell, and this resulting space in the synapse, and we really call this the neurotransmitters, are chemicals that diffuse across the synapse, similar to endocrine, and they affect the other cell. So similar communication system. This one takes time. This one is immediate. So recall that their reflex through loop has three components, right? We have the stimulus, we have the integration, and we have the effector. Okay, so let's think about an example. Okay, so our normal body temperature is roughly around 37 degrees, plus or minus. Okay, and so our set point is at that point. Now, let's say we have an external stimulus. External stimulus. So this external stimulus might look something like the temperature outside is minus 20 degrees Celsius because, we're Alberta. And let's say you forget a coat and you were out with your friends partying, even though you shouldn't have been because we're under COVID restrictions, and you decide that you're going to walk home, and you're doing it in the walk of shame because you don't have a jacket on, so it's shameful. Okay, so the temperature outside is minus 20. Our set point is 37, so it's going to cause us to cool down. So this, in essence, we know as the stimulus. So then we have receptors in our skin, and these receptors themselves are called thermoreceptors. Oh my God. What happened there? It's like a stutter when I wrote. Okay, thermoreceptors. There we go. Okay, so these are called thermoreceptors, and they're basically going to sense the temperature change. And they're going to send a signal through which pathways? The afferent, right? Because it's been affected to a integration center that we know as the brain. More specifically, the hypothalamus. And the hypothalamus contains the set point for our temperature. So then it's going to send a signal. It's going to determine, yep, something's going on. We need to send some signals out. So it's going to send out a few signals. The first signal it's going to do is it needs to warm itself up. So it's going to say to your cognitive side, you're cold. You need to put a jacket on or get warm in some way, shape, or form. The second component of this is it's going to send a muscle or a signal to your muscles, and it's going to tell them to increase production, and by way of shivering. So it's going to stimulate your muscles to rapidly contract and relax, and this is going to do what? It's going to increase our heat because of increased metabolism. Okay, and lastly, it's going to send a signal out to our blood vessels. Okay, so we have our blood vessels. And what they're going to do is they're going to constrict. So it's going to pull blood away from the core or away from the periphery, and it's going to send blood to the core to keep some vital organs alive. Okay. Once our temperature, by putting on a jacket and by increasing our heat production through shivering, and partially by this, and we get into a nice warm place and we warm back up, the stimulus goes away, and then this feedback loop ends. I'll give you guys a minute to kind of mow that down. So we just talked about internal, but what about external stimulus? Sorry, we talked about external stimulus. Now let's talk about internal stimuli. So you're probably like, what in the flying fornication are you talking about? Okay, so picture we have an invader. We have an infection. Okay, so this guy is going to meet his match. So we have these wonderful little cells that look like Pac-Man, and they're going to go and they're basically going to engulf this guy. These guys are called macrophages. Macro meaning large, phage meaning eat. So basically, large eater. Little cell after my own heart. Okay, so what's going to happen though is as this guy's feeding, he's going to have a little toot. So he's going to fart a little bit. And what he does is he produces a thing called a pyrogen. Okay, so what this does is this acts on the hypothalamus. And what it does is it changes the set point. And what does it change the set point to? Who knows? I mean, it varies depending on the type of bacteria, the type of macrophage, who the person is, genetics, etc. So, I mean, let's say it changes it to 39 degrees Celsius now. So now we were at 37 degrees Celsius, but now we need to go up to 39. So, same process occurs. Okay, so we have our hypothalamus, which is now going to send signals to our vessels through the efferent pathways. It's going to send a signal to our cognition. And if you're anything like me, you're going to take a really hot shower. And it's going to send a signal to our muscles to shiver. What does this constellation of effects sound like? Flu-like symptoms. The second most common call we go to in EMS.
Sick of those 36 cards.
36, 37, 32. All right. So when the body has a pathological condition, the body will try and ensure that, or it try to invoke change to get everything back to its normal. But when it doesn't recognize the normal as what is supposed to be normal, we get pathology. Okay. So it's trying to get itself back by a negative feedback cycle, but it's the wrong one. Okay. So eventually your body will get itself back to where it's supposed to be by changing its own set point. All right. So let's talk about specifically negative feedback loops. So loops that are designed to bring about an end. Designed to bring about an end. Okay, and it's designed to bring about an end of a or removal of a initiating stimulus. All right, so it can be simple, it can be super simple, or it can be crazy complex. So let's talk about one of each, shall we? So simple would be a low blood sugar. So this would be your stimulus. And then your receptor is going to say, is, again, your brain, or you have a receptor, that's your cells saying, I'm not getting sugar that I need. And, or I've eaten too much sugar, our sugar's low, we need to release more. So it's going to send a signal to the brain. That's going to send a signal down to your liver to release glycogen, and your body will convert it into glucose, which will increase your blood sugar, which will stop the stimulus. Okay, so you guys can follow that one super easy. I know you can. Let's talk about a complex one. So what happens in a complex one? We have cell A, and he is going to create a signal. So he gets a stimulus. And then he sends a signal to cell B, who sends a signal to cell C, who will eventually send a signal to cell D, and then he will send a signal to the target. Okay. Now the negative component of this is once cell D has sent his signal, he's going to send a signal back to cell C saying, you need to stop. And which cell C is going to send a signal back up to cell B, you need to stop. And then back up to cell A, yeah, we're all good. And so cell A sends a signal back to the stimulus saying, all good. So what can this look like in the body? Well, let's think about this. If we need to increase our temperature by way of metabolism, so we have a low temp, aka a stimulus. This is going to send a signal from our thermoreceptors to the hypothalamus. So he's already sent his signal off to the muscles and a signal off to the vessels. But now he wants to increase his metabolism as well. So the hypothalamus is going to release thyroid releasing hormone, which is going to act on the pituitary, which is then going to act on the thyroid. So the pituitary is going to release thyroid stimulating hormone. The thyroid is going to obviously release, T4, T3, whichever thyroid hormone there is. And then it's going to increase metabolism of other cells. So T4 and T3 act on all cells to increase productivity, thereby increasing metabolism. Okay? So eventually, as metabolism goes up and our heat is generated, then we get a negative signal from our cells going back to the thyroid, going back to the pituitary, going back to the hypothalamus, going back to our thermoregulation stimuli, okay, to negate that. And that, my people, is a negative feedback loop. So next we have the ever elusive positive feedback loops. And positive feedback loops, they don't really occur very often. And they never occur outside of female reproductive tract. So as an example, we have an endocrine cell. He's going to send a stimulus to a cell to secrete follicle stimulating hormone. What cell might that be? Anyone? Off the top of your head? Pituitary. All right. So this is going to secrete FSH, follicle stimulating hormone, and it's going to go to its target cell. All right. So then it's going to do an increase the sensitivity of other cells to increase the receptors available. So it wants to increase the sensitivity and increase receptors available. So then it's going to go back up to the endocrine cell with a stimulus saying, we've done this. Endocrine cell goes, oh, we need more FSH then, and it's going to continue. And we call this proliferation. This would be a menstrual cycle. So let's talk about control mechanisms. So most positive and negative feedbacks operate by turning things off. Okay. And so whether it's turning off or on, or turning off a hormone or not, that's what they're really referring to. Whereas tonic control is some referring to that is more of what a steady state is. So it's not equal on both sides, but what we're talking about here is we are actually talking about blood vessels. So we have this steady state, steady control of our blood vessels kind of at all given times. And what this is what this means, or sorry, what I should say is what this means is that this is essentially not fully relaxed, but not fully engaged. So we're at a tonic state. So there's tone, okay? Hence tonic. So there's tone to our vessels, and we're more particular, our arteries, okay? And what affects these is our nervous system. Moreover, our sympathetic nervous system and our parasympathetic nervous system. So what's going to happen, we call this state right here a basal state. Okay? And the basal state of contraction is typically influenced by the parasympathetic nervous system. Now, when the sympathetic nervous system kicks in, it's going to, let's say it increases, it's going to do this. We're all of a sudden going to get a rather constricted artery versus a rather somewhat relaxed artery. And yes, I'm very well aware that this looks just like a donut. And if we have our parasympathetic nervous system, it's going, if it has its way, it's going to have complete relaxation. And neither one of these, in of itself, outside of a pathology, is really that good. It's going to cause a lot of problems. Okay, so it's common of vessels, or the lumen of vessels will contract or expand and allow less or more fluid based upon the needs as indicated. So what's going to happen is, again, you have a stimulus for some reason that's going to say, I need more tone or I need less tone. Okay. And these are essentially what's going to happen. So the sympathetic is going to either reduce its output or the parasympathetic is going to increase its output. And that is what we call tonic control. Okay. Then we have another type of control. We call this control antagonistic. So as we discussed earlier, that antagonistic, that was that yin and yang, that back and forth by the parasympathetic and sympathetic nervous systems. Okay. And typically on the heart, We have input coming from both the sympathetic and parasympathetic nervous systems. They work in opportunistic, or they work in opposition. So they're antagonistic. All right. So they don't really bind to the same receptors, but they compete for that control. So we know that the parasympathetic nervous system controls the rate of cardiac output, or gets in control if the rate of cardiac output is way too high. If the cardiac output is way too low, we have the sympathetic nervous system that kicks in. Okay. And this is that antagonistic control. But this is what we mean when we're talking about a steady state. Okay. All right. So, in summary, the human body is an interdependent set of self regulating systems whose primary function is to maintain the internal environment compatible with all living cells and tissues, which we call homeostasis. Now, important generalizations of the homeostatic control systems. Stability of internal variables is achieved by balancing the inputs and the outputs to the body among the organ systems. In negative feedback control, is a variable corrected by bringing the body back into the initial set point. Note that set points can be reset at higher or lower physiological value. Remember the pathogen? And it's not always possible to maintain everything in relatively constant by homeostatic control mechanisms. There needs to be a hierarchy of importance. And there's two organs that always win out: the brain and the heart. Because we need the heart to move everything around to get stuff where it needs to be, and we need the brain to function everything else. So these guys are going to win out every single time. And that is your lecture for today.